Okay, this will be the last video in this particular segment of videos on triple integration, kind of rounding off our chapter. Please make certain that you are continuing to work on problems assigned by the class, that you're also working on your integrating abilities. The focus of these videos is about how to set up these multiple integrations, these iterated integrals. So here we go. We have a solid region, so we know it's 3 dimensions, bounded by x squared plus y squared equals 9. Because it's a solid region, that makes this a cylinder. Z equals 0, or the xy plane, is the bottom, and our standard cone is the other boundary. So volume's our goal. We'll get there. Let's look at the cylinder. Nothing too fancy about that. Notice I don't talk quite as efficiently while I'm drawing these. All right. There's the x-axis, and there's the y-axis, and there's the z-axis. And within this cylinder of radius 3, in other words, without the cone, there is no upper boundary. It extends forever. We have a cylinder, we have z equals 0, which is the xy plane, but we would have no top, so to speak. So the boundary is actually not the cylinder itself, but this cone. And so we could imagine it several ways. Let's make it solid. We're really looking at not what's in the cone, but what's outside of the cone. We're concerned with this region out here, the anti-cone, maybe. So there's certainly a way using geometric formulas to calculate volume. If you know how to calculate the volume of a cylinder and the volume of a cone, you could just simply subtract. So this is just about how to establish measuring a region for more complicated problems that follow later. So as usual, top view is one of my objectives. And the top view is a circle. And that's the y-axis and the x-axis. It happens to be radius 3, but that doesn't actually impact the way the spherical integration gets calculated. What we do care about is that this tells us that theta is from 0 to 2 pi. We then look at the side view. The side view, I've been using primarily just the z-axis and the y-axis. And the x-axis would be coming straight towards the camera. Theta takes care of the fact that we rotate around the z-axis. I just want to see what would it look like just from the side in the first octant. And what we would see is the cone, and then this side of radius 3. This is the region below the cone, but touching the xy plane. Remember, that's the x-axis. This is our region. And theta says, let's rotate this all the way around, making this solid. So the side view can tell us that phi, remember, we don't measure up, z-axis down. So phi begins its journey at pi over 4, and it ends its journey at pi over 2, or pi halves. All right, so I now have the limits of integration for 2 of the 3 integrals. I want to do one more rendition of the side view. Side view. Z-axis, y-axis. All right, theta is going to rotate it all the way around the z-axis. All the way around it will be rotated. The angle phi tells you how much down from the z-axis we go. So the question is, what are the values of rho? From where to where would the values of rho be measured? Well, rho is measured from 0 to whatever this side is. Please note that it's farther from here to here than it is from here to here. That distance is changing. There's gonna be a variable there. So I know this is 0, but what exactly is this value? Well, this vertical line is not a vertical line at all. It is the side of the cylinder. And the equation of the cylinder is x squared plus y squared, which is equal to 9. I need to somehow convert this to a rho equals equation. It's not one of the equations on my memorized list, but I do know how to convert. For instance, x squared plus y squared is r squared. And so therefore r is 3. I don't need to worry about the plus or minus 3 because theta will rotate around all the way around the z-axis. Angle phi keeps it above the xy plane. But r is equal to rho sine phi in our spherical conversion formulas. So therefore, rho equals 3 divided by sine of phi, or 3 cosecant of phi. And again, you have to make this moral decision. If you don't like fractions, then use cosecant. And if you don't like cosecant, then use the fraction 3 over sine. I don't mind either one of them, but I can see you wrestling over which one you'd rather write down. So we're ready now. Volume is equal to 1, 2, 3 integrals, rho squared sine of phi, d rho, d phi, d theta. My theta from 0 to 2 pi. My angle phi, pi over 4 to pi over 2. And finally, my value of rho from 0 to 3 cosecant of phi. And that, my students, is the volume of that region that is below the cone. So we've done in the cone, we've done with the spherical top, and we've now done below the cone as some fairly common shapes that you would generate by rotating around an axis. Depending on the function that will be in here that we're integrating with later, you would choose spherical if it gave you some sort of an advantage for integrating the whole problem. All right, that's it for now.